Hello everyone. Let us quickly do a recap of the things that we have learned in the previous modules. So we have learned how to do iterated elimination of dominated strategies, and we have also seen that in doing so, how the equilibrium are being preserved, what kind of equilibrium are preserved. Then we also looked at the notions of stability and security, and we have seen that these two ideas actually coincide in the case of that special game called the matrix game. Now, so far what we have discussed is only related to pure strategy. So player can either pick strategy L or R, but those are called the pure strategies because you are either picking one strategy or the other. So we have also seen examples like this one, that if you look at the notions of equilibrium in this pure strategy world, then you might not have an equilibrium. So this game is an example where pure strategy Nash equilibrium does not exist. Now, in order to guarantee what kind of outcome we can expect in this kind of games, in this module we are going to expand our equilibrium notion, our strategy notion, to something which is known as mixed strategies. Simply put, mixed strategy is a probability distribution over the set of strategies. So if you look at the strategies, the pure strategies of player 1 was L and R. Now you are putting certain probability on top of each of these strategies, similarly for player 2. And we'll call this probability distribution 2/3 and 1/3 as the mixed strategy of player 1. So in order to make this idea a little more formal, let us introduce some notation so that we consistently use the same thing. So let us consider a set A, and for most of this lecture and in this course, we'll be only dealing with finite sets of actions. So therefore, consider a finite set A, and by this notation, delta of A, we are going to denote all the distributions on this finite set A. So what does that mean? So this set is essentially the collection of all those vectors. So notice that this vectors P has the length of the size of this set, finite set. So let's say if there are m elements in this finite set, then the length of P will be m. And each of those numbers, each of those entries in that vector is going to be filled up by some number which lies between 0 and 1. And with the additional constraint that all these values, when you take the sum of all the components of this vector, it will be equal to 1. So that is the standard definition of any probability distribution. Now, when we define mixed strategy, it is nothing but a probability distribution over this strategy space of a player. So sigma I, we will call that as a mixed strategy of player I, and we will denote that as sigma I belonging to delta of Si. So Si is the strategy set of player I, and we are going to assume that the strategy sets are all finite. Therefore, you have, according to the previous definition, sigma I is a probability distribution over these strategies of player I. And this is what it says formally. Now, since we are considering only non-cooperative games, the players choose their strategies independently. So player I is not cooperating or communicating with player 2 when making his or her choice of actions. So therefore, all these strategies are sort of independent. What that means in the context of mixed strategy is the joint probability when you are looking at the joint outcome, because all our final guarantees will be with respect to the joint outcome. So player 1 choosing some strategy, player 2 choosing some strategy, and when both of them choose a particular strategy, we are going to talk about what will be the utility of player 1 or player 2. Now, according to that, when player 1 is picking S1 and player 2 is picking S2, the probability of that happening is going to be just the product of their marginals, and this is because these players are picking their actions independently. So there is no joint distribution. The joint distribution actually decomposes into the product of marginals. Now, so using this property, now we can actually write down the utility of a specific player at a mixed strategy profile sigma I sigma minus I. So again, very similar to the strategy profile, the pure strategy profile, we are going to now write sigma I sigma minus I as the mixed strategy profile. So, and we are going to denote that as the utility of sigma I, utility of player I at sigma I sigma minus I. And what it means is, let's start from the innermost element. So we have this utility of player I when player 1 to n are choosing strategies S1 to Sn, and then multiplying by corresponding probability masses, sigma 1 of S1, that is the probability with which player 1 chooses strategy S1, probability of player 2 choosing the strategy S2, that's the probability, and the joint probability is just the product of all these things. So we are multiplying the utility of those pure strategy profile with the corresponding probability, and then taking the sum over all strategies. So this is essentially going to be the expected utility when all the players are picking these mixed strategies. Just to note that we are actually overloading this notation of UI. So ideally, so this utility is denoting both the utility for pure strategy profiles and also for mixed strategy profile. Ideally, you should have used a different notation, but I think in this context, it will be clear whenever we are using the pure strategy or mixed strategy profile, and therefore we don't really need to use a different notation. As we just said, that utility at a mixed strategy profile is going to be the expectation of the utilities at those pure strategies, and because it's an expectation, all the usual rules of expectation will also hold. For instance, linearity of expectation, that is something that we'll be using very often whenever we are talking about mixed strategies. So let's talk about an example to understand the idea of pure strategy, the mixed strategy better. So this is the original goalkeeper and shooter game. And let us assume that this player 1 is choosing the strategy L and R with probabilities 2/3 and 1/3 respectively, and player 2 is choosing the strategies with probability 4/5 and 1/5 respectively. Now what we are going to say is the utility at this mixed strategy profile. So notice that sigma 1 in this case is this vector of 2/3 and 1/3, and sigma 2 is essentially this vector. So we are going to find out what is the utility of player 1 when this mixed strategy profile has been chosen. So 2/3 is the probability that has been chosen. So we are going profile wise, so pure strategy profile wise. So let's consider the first entry as L comma L. So that is the first pure strategy, and the probability with which that strategy profile is picked is 2/3 times 4/5, because player 1 is going to choose L with probability 2/3 and player 2 is going to choose L with probability 4/5. We are multiplying that is the probability that this strategy profile will be chosen, and player 1 gets -1 of reward utility in this case. Similarly, you can find out LR, so that is 2/3 times 1/5 multiplied by 1, and similarly you can fill it up. So this is for the first one was for L comma L, this was for L comma R, this is R comma L, and this is R comma R. So these are the probabilities, and then these are the utilities at the pure strategy profile. So this the total number will be the expected utility of player I when this mixed strategy profile has been chosen. And just to end with a note that you can actually think about mixture of multiple mixed strategy. So this is essentially going one step forward. So suppose player 1 has one strategy, one mixed strategy sigma I, the other mixed strategy is sigma I prime, and it is mixing these two strategies to mixed strategies. And because of the linearity of expectation, you can find out that this will actually come out to the corresponding sum of the individual utilities.